Hello, everyone. So we're going to go over a very short section, but an important one, where we're going to talk about all the possible bad cases, okay, that you can face when you're computing a limit. So far, of course, we looked at bad boundaries. So bad boundaries are a problem of the form either the square root of 0 or in general an even root, so fourth root, sixth root of 0. So if you plug your number in, you have a limit, left, right, or two-sided, doesn't matter. You plug your a inside, you get the square root of 0 or the even root of 0. That's bad. Okay, that's a bad boundary problem. If you plug your a and you get a division by 0, so when I say division by 0, it's always a non-zero number divided by 0. That's also a case of a bad boundary. Of course, the proper terminology is indeterminate boundaries, but I just hate saying it. And we've seen these two cases for the square root. That was what we dealt with in section 2.7. Division by 0, this is what we dealt with in section 2.9. And there's another one, another bad boundary that we'll see later in section 2.13, which is ln of 0. So if you have like a limit, you plug your a and you get ln of 0, that's also a bad boundary case. And for all these cases, okay, what you have to do is you need to plug in a minus or plug in a plus, depending on if your limit is a right limit. So if it's a left limit, you're going to plug in a minus instead of a. If it's a right limit, you're going to plug in a plus instead of a. And if it's a two-side limit, you need to do both and then compare. Okay, so it's the same strategy for all these three bad boundary cases, but there are other bad forms that we're going to face. If you plug your number a for a one-side limit, two-side limit, or a one or two-side limit, if you get infinity minus infinity, that's really bad. If you get 0 over 0, that's really bad. I just realized I skipped over my second case. If you get infinity over infinity, that's really bad also. If you get 0 times infinity, who wins here, the 0 or the infinity? We don't know, so that's a bad cases. So you need to be able to see this. Like you're trying, to be quick and efficient. You plug your a in, you get an expression where you have a 0 times infinity. Shit, okay, that's a bad cases. If somewhere you get 1 to the power of infinity, that's also a bad case. 0 to the power 0, that's a bad case. And infinity to the power 0, that's also a bad case. So the point of this section is just to be aware of that. So the ultimate strategy when you're computing a limit in general is just you plug your number. So you plug your number, one-sided or two-sided limit, you plug a in, and you hope that using the basic laws or the basic infinite laws, you will either get the answer or, and that's of course what will happen in most questions, you will identify the bad form involved in your limit, and then according to, is it a bad boundary or is it a bad indeterminate form, depending on your function, there's a couple of things you can check, and then you will use the proper solution to find the answer of your limit. Of course, here I'm just listing all the bad cases, but why are those bad cases? I'm not going to go through all of them, but I'm going to explain to you why for one of those indeterminate form, why is it bad? The thing that is crucial to understand when you're computing a limit, you're not just evaluating a function. You're really looking at numerical behavior for many inputs that are getting closer to a number from the left or the right side, or that are getting bigger and bigger if you're going to look at a limit going to infinity, or bigger and bigger going to minus infinity. So you're looking at a bunch of numbers and you're looking at the behavior of these numbers. Are they approaching something? Are they blowing up? Are they just oscillating? So for example, just a quick example, I'll just do that for 0 times infinity, but the same sort of ideas can be applied for all those bad cases. Why is 0 times infinity 0? So here the idea is, let's compute sequences of numbers. Let's produce sequences of numbers where one of them goes to 0 and the other one goes to infinity. And let's look at what happens if you multiply them. So for example, suppose I have this first sequence. Okay, suppose my first sequence here is the following. 1, and then I'm going to look at 0.1, 0.01, 0.001. You get the idea here. That sequence is getting closer to 0. And now let's look at this second sequence. Let's look at one that goes to infinity. So for example, suppose I have 1, and then I have 10, and then 100, and then 1,000, and etc. You can clearly see that these numbers are getting bigger and bigger. They're going to infinity. Now, what happens if you multiply both? What happens if you go 1, the first sequence, and you multiply it by the second one? So let's multiply the first one. So the first sequence times the second sequence, and see what do we get. So if I multiply these two numbers, 1 times 1, what are you going to get? Well, you're going to get 1. If you go 0.1 times 10, you're going to get 1. If you get 0.01 times 100, you're going to get 1. If you look at 0.001 times 1,000, you're going to get 1. And of course, where are these numbers going? Well, these numbers are going to 1. So you have the sequence 1, 1, 1, 1, 1, 1. If you have a table with a bunch of 1s, you're going to conclude that this is going on to 1. So if you are multiplying 0 times infinity, you could kind of conclude, well, if you have 0 times infinity, it must be 1, which is kind of weird because you thought that maybe 0 times infinity, like 0 times nothing is 0, or infinity times any number is infinity, but we just don't know. Let's look at another sequence. I'll just call that 1, because I'll always use the same 1 going to 0, but I'll use another 1 for the one going to infinity. So for example, suppose my first sequence, suppose I have the following sequence now. Well, let's just rewrite it. So let's say we have the same first sequence. So here we go. You copy. Boom. Okay, so the same sequence going to 0 here. So it's the same number 1 here. The one that is 1 times 0.1. 1, 0.1, 0.01, 0.001. And now, okay, so what we're going to do is produce another sequence. So I'm just going to call that one the third one because it's different. So let's look at this sequence here. Suppose now I am looking at the sequence going to infinity, but suppose it's 1 to start with, then it's 100, then it's 10,000, and then 1,000,000. How many zeros? 1,000,000? 6. So 1,000,000. So of course you see these numbers are again going to blow up to infinity, but they blow up to infinity way faster. So now what happens if you multiply 1 times 3? Well, if you multiply 1 times 3, so again here 1 times 1 will just be 1. But now 0.1 times times 100 is going to give you 10. 0.01 times 100, times 10,000 is going to be 100. And 0.001 times 1,000,000, this is going to be 1,000. So you see the pattern here. These numbers, where are they going? Well, they're going to infinity. So this product here is now going to infinity. So this 0 times infinity blows up to infinity. So basically when you are multiplying 0 times infinity, you just don't know. It really depends on which one goes faster to infinity or which one goes faster to 0. Sometimes if they kind of go as fast together to like in parallel 0 to infinity, you're going to go to a number. If the one going to infinity blows up to infinity faster, then this product will blow up to infinity. And we could also have an example where the sequence goes to 0 faster and then the product would be 0. So when you have 0 times infinity, is it 0? Is it infinity? Is it a number? You just don't know. And this is why we need to find ways to go around this bad form. And this is what we'll do later. But now the focus is more, okay, we see it's a bad form and we have to be ready for it. And then what do you do? Well, it depends. Okay, so anyways, for this short section, just be aware, 3 bad boundary form, okay, root of 0 or even root of 0 in general. A non-zero number divided by 0, this is what I refer to as division by 0, and ln of 0, so that's for later. And there's all those bad cases that you need to be aware of from now on that are not basic infinite laws whatsoever. Infinity minus infinity, infinity over infinity, 0 over 0, 0 times infinity, 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. Those are 7 deadly sins, okay, of limit computations, and we need to learn how to go and face them. Okay. Anyways, for that section, that's it. Okay. Bye-bye.